So I just want to recall a little bit of what we did last time. So let me recall. So what we're doing is I defined what linear models were. So I defined what a linear model is. And the way we thought of it was it's a data set with n data points, n observations. Let's say y1 through yn, y1, y2 up to yn. There are n observations. You can think of it as n observations. So this is what we typically call as the data. And then you believe that that they're related to some other parameters in the model, like so the parameter space is beta 1 to beta n. So let's say beta 1, beta 2, up to some number beta sub m. So the m need not be equal to n, and these were the parameters of the model. Right? And we assume that the distribution of the data was modeled by the following equation. So we thought yi was equal to, so we had an equation for in terms of the linear combinations of all the beta m's. Let's say yi is equal to summation j equal to 1 to m, and then we had the beta j, sorry, each of the beta j's, and then we had a specific linear combination with regard to the yi. It's called xij, and then plus we assumed it's a random model, so we gave it an error epsilon I. And this was the model we assumed for 1 less than equal to I less than equal to n. So this is what we called as linear model. And what were epsilon i's? So let's say, let me mark epsilon i's. So epsilon i's were so as of now, I didn't assume anything about them. I just said they are uncorrelated random variables. And I gave it a certain variance structure. So, and then I assume mean 0. And I gave it a variance structure. The variance structure I gave it was sigma squared. So this is what I called as the basic linear model that I had in mind. But of course, there was a way of setting it up. But another way to think about this whole model is that if I think about the little bit model, I could think of this equation instead of in this fashion. I could think of it as data points yi being random, and I could just say that E sub yi was just summation j equal to 1 to m xij beta j. Make it a little small so I can put everything in one space. And once I specify the mean, all I have to say was how the yi's are correlated or uncorrelated. I just say yi's are uncorrelated. So these are yi's. And I would say yi's mean is this. They are uncorrelated. And the variance of yi is sigma squared. Okay. So this is an equivalent way of preserving the linear model structure. Make it a little smaller and a little box I can put in the same space. And the last thing I did last time was set up the notation for this. I said that I would think of my vector y as y1, y2, yn transpose. I would think of it as a column vector. Similarly for the beta as well, I would think beta bar as just beta 1 up to beta sub m transpose. Right? And I would think my entire vector x as just a bunch of xij's. I would think of xij's y1 less than equal to I. So for that, 1 less than equal to I less than equal to n, and 1 less than equal to j less than equal to n. And I would think of my vector epsilon random variables as just a row vector or a column vector, epsilon 1, epsilon n transpose. And the way I thought of my linear model was I said I would think of my model as y is equal to x beta plus epsilon. So there's another way, the third way of describing the linear model. So I kept saying that last time that I would just always write my linear model as just three parameters. One is y, one is how the mean behaves, that is x beta, and how the variance behaves, I'll just write it as sigma squared times I n cross n. Right? That would give me the entire description of the mean. Right? So if you sort of unravel this is your data, right? And this is your mean vector, right? Your mean of y, and this is your variance. So you could think of it as variance covariance matrix. Very nice. This is what we did last time. So that's where we are. And I discussed when things were estimable and not estimable and so on and so forth. Okay. So today I'll begin with just three examples, and then I'll go on to how to estimate the parameters in a second. So let's go to Siva. So there are three examples to keep in mind for this class, and we'll come back to them again. We'll come back with real data sets very soon. So the first one is called a one-way classification model. So a one-way classification model. And here what the model is it's parameter a little differently. So I'll think of it as yij is equal to mu plus mu I plus epsilon ij. And this is how I start off with it, remember? And then here think of it as 1 less than equal to j less than equal to ni, and 1 less than equal to I less than equal to, let's say, some number k. Right? So I thought of it as k populations, and each population I'm observing ni samples, and I'm doing this. The second model that I will come and play with quite regularly is called the nested classification model. Nested classification model. So in this model, what one does is one has a little tweak to the one-way classification. Here, assume that the within groups sort of little bit classified. So y I j k is the same as I have the same mean mu overall plus an intergroup effect mu I. I have two sources of randomness. One is delta ij within I and j, and then I have an epsilon ijk. Okay. And here I do the same thing. I have 1 less than equal to k less than equal to nij, and then I'll have a 1 less than equal to j less than equal to mi, and I'll have 1 less than equal to k population as before. The third example is what's called a two-way classification model. Classification model. Here in this one, I have I just do a little bit everywhere. I have a little pairing, so I'll have a yijk again. Right. I'll have a mu. I'll have an alpha I for the ith group. I'll have a beta j for the bth group as part of the mean. I'll have an error gamma ij, and I'll have a plus an epsilon ijk. That's the randomness. And again here I'll have 1 less than equal to k less than equal to nij, and I'll have a 1 less than equal to j less than some capital J, it can go independent of I, and then I'll have a 1 less than equal to I less than equal to some number capital I. Very nice. So these are three types of examples that we should keep in mind, and as I go along the class, I'll come back to them again. I'll try to deal with them. So today I'll begin with what's called least squared estimation. So let me start the topic today. So I'll call it least squared estimation. I'll do normal equations today. So least square. So here what happens is that I'll take a linear model and I'll prescribe a way how to estimate parameters, right? So let's start again. So one exercise I did not do here. Let me just go back once more. So one exercise to do, all of you can try, is the following. You can express 1, 2, and 3. So express 1, 2, and 3 as our usual way, as a y vector. Find out what the x vector is, what the beta is, and what the epsilon is, or the variance is. Sorry. Yeah, our epsilon is the random numbers. So we write the answer epsilon, write down what the covariance matrix is. So I'll call it as sigma squared times I. So you should find out what these guys are for these three examples. So I'll go back to my old notation of linear model. So I'll take suppose I have a linear model like this. So suppose I have y, I have x beta, and I have sigma squared I n cross n as a linear model. And I have to define what I mean by a least squared estimate. Okay, so I'll define, let me write definition down. So definition. So a random vector, so now again the vector is random, so as of now, so a random vector beta hat, right, belonging to, let's say, beta hat bar belonging to Rn, in my case, right, Rm, is called a least squared estimate of beta. So beta is the thing in the linear model, the parameter space, if the following is true. If I take y, I subtract x beta hat that I have, I take its L2 norm, right? And I want this to be the minimum or all possible betas that I have in Rm. I look at how far my x beta is from y, and this should be larger. L2. So anybody else should beat my y minus x beta hat. That means that's when I say my beta hat is my least squared estimate. So maybe I'll call this as pink, that way it's clear. So estimate is this, if this expression right here on this side is the smallest among everybody. So let me just, since this is maybe a linear algebra is a little bit, so I'll just recall what linear algebra, that if I have a vector, let's say z in Rn, then the norm L2 norm of z, or is just the square root, the Euclidean distance, right, from the origin, I equal to 1 to n of zi squared. So that's just a notation. So I want the L2 distance between y and x beta to be this x beta hat to be the smallest among all possible parameters base beta, right? So just a remark. So let's call this as equation star. So what does star require? Star requires that x beta hat is closest to y among all possible choices of x beta with beta in Rn. And the closest is just the way we define closest is just in the L2 metric, right? The closest is, so by closest you mean in this, let me circle it out. The closest is in this distance, right? And x beta hat is your least square estimate. Very good. Of course, I have just said it like this, but somehow one doesn't, if a least square estimate exists, can I always find it? That's not clear, but I just define it like this. I have to find the closest one to y, the vector 1. Very good. So that's the definition of a least square estimate. So there's one small generalization. So this is just if you have a parametric estimate, like we discussed last time. So there, so then typically you take a linear parametric function, let's say, linear parametric function. If you take P transpose beta hat, that's the least squared estimate. So the function P transpose beta. Then for this particular thing, the least squared estimate is P transpose beta hat. Okay. So now I'll state one fundamental theorem that we will prove now for this class. And then of course we'll require some linear algebra, so I'll try and go over it slowly. So the first theorem we'll prove today is the following. Theorem is the following. So let's consider a linear model. Consider a linear model. So let's call it as y, x beta, and epsilon. Or not epsilon, I should specify the variance covariance matrix. So I'll call it sigma squared I. That's my linear model. And it's crucial. It's a nice theorem. Then, so it doesn't say it always exists. All it says is the following. Then any least squared estimate beta hat of the parameter beta, that is the one that minimizes the L2 distance from y of x beta, satisfies x transpose x beta hat is equal to x transpose y. So I'll come back to this equation. I'll call it equal. I'll give it a name, equation 1. I'll come back to it again. So the name of equation 1, so let me write this name in now. The name of equation 1 is called normal equations. One is called. So I'd like to, but formally speaking, the least squared estimate is the one that minimizes this L2 distance. So it's this closest vector beta hat, so x beta has closest to y in the L2 distance. And we'll try and see how the significance of this, what this thing is after I prove the theorem.